Let's make a start for the November 2024 meeting of the Mornington Peninsula Astronomical Society, as they all come hurriedly in. A few things to mention here. The first one is at the centre at the top there. Monash University, in conjunction with scientists in Germany, have actually looked at how long it took the solar system to form, 4.6 billion years ago, and based on the radioactive decay of thallium to lead in the pre-solar grains that they have samples of, they've determined that it took only 10 to 20 million years for the solar system to actually coalesce and the sun to actually form, which is very, very quick, and that it actually came from the remnants of a red giant star that puffed off its outer layers, and that's where that all came from. Down the bottom in the centre there was showing the second Starship chopsticks attempt. It was on the news this morning, and they aborted the second attempt at catching it. Although I did see something on Facebook this afternoon by one of the astronomers at ANU saying that they were doing another chopstick one tomorrow morning. So I'm not sure whether he's just got the day mixed up and he's missed it by 24 hours, but I'm pretty sure I saw on the news this morning them getting ready to have the second attempt, and they ended up ditching it in the Indian Ocean, from what I remember seeing. Yeah, could be. Over on the top on the right-hand side there, RMIT is leading the charge with the Australian National University and University of Queensland. They're going to be launching seeds and plants up to the moon to see which ones will be suitable for growing and harvesting on the moon. And that's called the Aleph mission, and that's due to launch next year, 2025. So Australia's been given the task of doing that one. And in the middle, in the right-hand side there, showing a dung beetle doing its work. Swedish researchers actually found that the dung beetles navigate of a night time by using the Milky Way. So they work out direction using the Milky Way in the sky, so they sense that. Bearing that fact in mind, the University of South Australia has actually developed a Milky Way tracker that they intend to do the same sort of thing for deployment on small satellites. So sort of acting as a backup navigation system. Now, I don't know whether the word dung actually appears in the name of their gizmo that they're going to put on the satellites, but there we are. You never know where it goes. And finally, down the bottom right, the University of South Australia and Google are working on a constellation of 52 cube satellites. In other words, they're relatively small satellites going up into orbit, and the idea is to be able to detect bushfires anywhere on the planet that once they get to a size of 5 metres by 5 metres burning, they'll trigger an alarm automatically, and hopefully authorities have something there to actually jump on them before they grow too big and get out of hand. So tonight, welcome everybody. Normally I'd read out a list of new members, but our secretary hasn't arrived yet, so with them. So if she comes a little bit later, I'll read them out. If there's any relatively new members here, we'll therefore read out your name at the next meeting of the Society instead. I'll then look very briefly at the events of the past month and the coming month. We'll look into the Ig Nobel prizes for 2024. And you may or may not be familiar with the Ig Nobel prizes. These ones tend to be a fun parody on some of the more famous scientists in the world, and they come out once every year. And I'll hand over to Chris to do the Astromofo, and Guido for Sky for the month, and then we'll look at the weirdest stars in the universe. And finishing off towards the end of the evening, we'll look a little bit at the Europa Clipper mission. That was the one that launched last month, and where it's possible that it may detect evidence of life potentially beneath the frozen ocean, although it doesn't have the capability to actually drill down into that ocean on that mission. And then we'll look at why Uranus spins on one side. Recently we had the Telescope Learning Day, and shown in the background there is a picture of I think Sylvie there in there showing her telescopes to everyone. And it's a little bit fuzzy, but maybe that's just my eyesight. And unfortunately we only had about half the number of people booked actually turned up on the day, and we're sort of a bit bemused as to why that was. It may be the fact that it was 99% cloud turned them off. But nevertheless, for those that turned up, it was a good event for everyone. Then a couple of days later, we had 2 school nights here. They were in camp next door here at the Briars, Yarra Valley Grammar. And unfortunately, they were completely clouded out on those 2 nights, but we had a good time with them, answering all their questions. The final Scouts, Cubs and Guides night was here. They were a bit luckier. They had no cloud whatsoever, and it was a very good evening for them. Committee meeting was just basically around upcoming events and planning everything to do with the calendar, especially for next year. 1st of November, the public night, Manfred gave the talk, and again, no cloud, so very, very good outcome there. And then we had one more school next door, actually at the camp as well, St Michael's Primary, Year 3 pupils, and again, they were fortunate enough to have no cloud. Now, coming up soon, first of all, I'll mention over on the right-hand side, we've got the, at the top there, the first calendar of images by MPAS members shown there, and that's available for sale outside if we can find someone to actually take the money tonight. And down the bottom, the almanac, which is the last edition that will ever be produced of this annual almanac, to the best of our knowledge. Astronomy 2025, and we do have some, I think we've still got some copies of that left as well. So if you're looking for something for Christmas, the calendars are $20 and the almanac for members is $25. Committee meeting will be next Wednesday by Zoom online. Then the public night is booked out at the moment, and Trevor's due to talk there. He's currently on the high seas, but he should be back in Australia by then. Then on the 7th of December, we've got the Christmas concert here with the Southern Peninsula Concert Band. That's where, if the weather's a bit inclement, they get set up at the front of the room here, and the audience is at the back there, and we try not to damage anyone's eardrums from the level of noise that comes from them. So at the moment, we've got 67 booked for that. So if you're interested in coming along for that and you haven't booked, I'd advise you to do so online relatively quickly. A week later, we've got the big Christmas dinner here at the Briars. Still, we've only got 29 booked for that so far. This is where members get effectively a roast dinner, and there'll also be some presentations of new life members of the Society at that dinner as well. Now, that's the last formal gathering of the Society for 2024, and we certainly recommend that to everyone, because it's a good way of getting to know everyone else who comes along to that. And some people only come along for that dinner in a given year. Cosmology group doesn't meet until just before Christmas on Saturday the 21st, but they are going ahead. And then in January we've got first Friday, first Saturday, second Friday and third Friday are public viewing nights, and they're already starting to book heavily for that one. And the next of these monthly meetings will be in January, so there isn't a December one of these meetings ordinarily. Right, now we'll jump into the Ig Nobel prizes for 2024, and each year they honour scientific achievements that first make people laugh and then make them think, and are usually presented by past real Nobel laureates from the Nobel Committee from Sweden. Prize money is $10 trillion, and that's Zimbabwe dollars, unfortunately, not Australian dollars or US dollars. So they do get presented with $10 trillion, and they have to present their work in a couple of minutes. And I'll show you an excerpt of some of the presentations, and you'll see what happens if they start to run over time on their presentations. They have a unique way of handling speakers that talk for too long, and it's hosted by Mark Abrahams.
The winner is from the USA. The Ig Nobel Peace Prize is awarded to the late B.F. Skinner for experiments to see the feasibility of housing live pigeons inside missiles to guide the flight paths of the missiles. Accepting on behalf of B.F. Skinner, here is his daughter, Julie Skinner Vargas.
On behalf of my father, B.F. Skinner, I want to thank you for finally acknowledging his most important contribution.
The Ig Nobel Demography Prize is awarded to Saul Justin Newman for detective work to discover that many of the people famous for having the longest lives lived in places that had lousy birth and death record keeping. Prize is presented by Nobel laureate Ricky Boendi.
Okay, I was working away in my little lab, undisturbed by bunkum and woo, when I was told the way not to get old was the Blue Zone's lifestyle breakthrough. At a stroke of a pen, they had solved medicine and shown how geriatrics keep breathing. Long living, they said, in the abstract I read, had as a secret of heavy inbreeding. And when that didn't sell, they thought grandly, well, we shall play out the long game in sales, and went searching about for a secret to tout us, a way to outlive all the whales. But the secrets fell over like a lover in clover when I checked the government books. The Blue Zones are poor, the records no more, the 100-year-olds are all crooks. So the secret, it seems, to live out your dreams and make sure you keep living, not dying, is to move where birth certificates are rare. Teach your kids pension fraud and start lying. And I'd like to thank my mom, my dad. I'd like to thank all the old people who are collecting the pension while they're dead. It's really excellent work. I'd like to thank the world's oldest man for having 3 birthdays. I'd like to thank the...
Stop.
Okay.
Stop. I'm bored. Please stop.
The Ig Nobel Botany Prize is awarded to Jacob White and Felipe Yamashita for finding evidence that some real plants imitate the shapes of neighboring artificial plastic plants. The prize will be presented by Robert Merton.
As this research was based on a plant who can mimicking the leaf of other plants, and we just use a plastic leaf, and this plant mimic the plastic leaf. And how they do that? Our hypothesis is this Bokila plant have some sort of eye. They can see what's going around. And how they do that, we have no idea. And we need to continue studying on this plant, but to study on this, I need a position. So I just finished my PhD, and I need a job now.
The Ig Nobel Anatomy Prize is awarded to Marjolaine Willems, Quentin Henoch, Sarah Tanon Delara, Nicholas Kogan, Vincent Fleury, Romy Reysiguier, Juan Jose Cortez Santander, Roberto Requena, Julian Sterneman, and Roman Hossein Konsare for studying whether the hair on the heads of most people in the northern hemisphere swirls in the same direction, clockwise or counterclockwise, as hair on the heads of most people in the southern hemisphere. The prize will be presented by Nobel laureate Abhijit Banerjee.
we warmly thank the scientific committee to have chosen our publication about genetic determinism and hemisphere influence on her world direction. So to make a long story short, it began with the observation of my own twin identical daughters. When they just were born, I observed the same direction of the world, but one left-sided and the other one right-sided. So I decided to investigate, and I called my friend Hossein.
Yes, so we found interesting results on twins, and then we decided to check this quite a strange hypothesis, whether they would turn in opposite direction in the northern and southern hemisphere. So then we started working with colleagues from Chile, and we realized that in fact they do. It's nearly clockwise for everyone, but.
I'm bored.
The Ig Nobel Medicine Prize is awarded to Lieven Schenk, Tamine Fadey, and Christian Buchel for demonstrating that fake medicine that causes painful side effects can be more effective than fake medicine that does not cause painful side effects. The prize will be presented by Nobel laureate Esther Duflo.
So we actually investigated if side effects and how they actually can improve treatments. And although this sounds very counterintuitive, in some cases, previous to research on placebo effects actually suggests that this is the case. So we investigated it, and we found that this is the case, that non-painful side effects can actually lead to a bigger pain reduction. And yeah, if you're interested in the details, I have to refer you to the paper.
The Ig Nobel Physics Prize is awarded to Jimmy Liao for demonstrating and explaining the swimming abilities of a dead trout. The prize is presented by Nobel laureate Mugu Oendi.
I discovered that a live fish moves more than a dead fish. But not by much. Not by much. A dead trout towed behind a stick also flaps its tail to the beat of the current like a live fish, surfing on swirling eddies, recapturing the energy in its environment. A dead fish does live fish things, using its body like a sailboat to tack upwind, its torso undulating, acting as a lift-producing sail and a stabilizing keel at the same time. Fluids flap flexible fish forward from forces and feedback. The water swims the fish. A flaccid trout ignited my career, and I'll forever be grateful.
The Ig Nobel Probability Prize is awarded to František Bartoš, Erik Jan Wagenmakers, Alexandra Sarfoglu, Hendrik Godman, and many colleagues for showing both in theory and by 350,757 experiments that when you flip a coin, it tends to land on the same side as it started. Prize will be presented by Nobel laureate Asha Banerjee.
So we flip coins over 350,000 times, which means 650 hours of constant coin flipping, or about 81 work days. It might seem ridiculous at first, And perhaps it was.
We wanted to test a prediction from Diaconis, Holmes, and Montgomery, who argued that when people flip coins, the coins wobble in the air. Because of this wobble, coins presumably tend to land on the same side they started. But the effect is very small, possibly only 1%.
We found compelling evidence for the effect. Also, some people show effects larger than others. Finally, there seems to be learning effects, and the more coins you flip, the less biased you become.
So we would encourage everybody to pick up this fascinating line of research and maybe attempt a replication of our experiment as well. Good luck.
We are with Astromofo number 19. Comet C 2023A3 Tsuchinshan Atlas. So the Astromofo is the monthly challenge where we pick an object or a subject and members photograph that target. And the one for the last month was the comet that was in the sky, and you would have all seen quite a few photos of it. This image here is by Chris Black and was taken early morning on the 30th of September with his William Optics Red Cat, Red Cat's got a focal length of around about 250 millimetres. Initially the comet was visible early in the morning until it went into conjunction with the sun, between us and the sun, and then it became visible in the afternoon after that. Okay, Comet Challenge was completed by Chris Black, Steve Wilkins, David Rolfe, Nerida Landcake, Mark Hillen, Greg Walton, Kelly Clitheroe, Ben Claringbold, Jamie Pole, Chris Kostokanellis, Guido Tack and Sylvie Grandit. And this image, so we've got a pretty good turnout this challenge with quite a few photos. And this one here was by Steve Wilkins, photographed at Cape Schanck. So you got the comet, really nice long tail again in the morning. And the way that I've ordered the rest of the photos is chronologically. So you'll see them by date from the earliest to the latest, the last photo that was taken of it by a member, with exception of these first two. Actually, they're not too bad, 28th of the 9th. Okay, next slide. I've got a bit of an animation which shows the trajectory of the comet just as it was coming into the inner solar system. So the circles that you see around there are the inner planets, starting with Mars on the outside, then Earth, Venus, Mercury, and the Sun in the middle. And the purple dotted line represents the trajectory of the comet. And this animation is from Wikipedia. So the comet, the orbital plane of the comet is fairly inclined with the ecliptic. It's around about 139 degrees. And what that means is the orbital plane of the Earth relative to the comet, it's 139 degrees. Being 139 degrees means that it's gone past 90 degrees and the comet has a retrograde motion. So you can see that the planets are orbiting in one direction, the comet seems to be orbiting in the opposite direction to the planets, and you can see those lines coming off it are its height above the ecliptic plane, so it's quite elevated and it's nowhere near the Earth's plane of orbit. So this is an Oort cloud object, so it originated way out in the further realms of the solar system. And obviously inbound, as we can see, it's on the right side of the sun, which makes it a morning object. When it goes outbound, it's on the left side of the sun compared to the Earth, with a blue dot there, and then it becomes an evening object. Okay, next photo we've got is taken by Dave Rolfe on the 28th of September again from Mount Buller. Single 20mm shot with his Pentax, and you can see it's got a really nice long tail. So coming inbound and leading up to its closest approach, it really had a really nice long tail, which was visible in a lot of the in the photos. And this one was just after perihelion, which was on the 27th of September. So the comet's closest approach to the Sun was on the 27th of September, and it came within about 0.39 astronomical units of the Sun, which is just outside the orbit of Mercury. Another shot here by David Rolfe as well from Mount Buller. This was during a public event at Mount Buller. This one is with a 250mm lens off a tripod, and that's 5 10-second exposures which were stacked. So really nice shot and really nice long tail there with the comet. So the comet was first discovered by the Purple Mountain Observatory in China, which is also known as the Zijinshan Astronomical Observatory. When you anglicise it, it becomes Tsuchinshan. So that's where the Tsuchinshan comes from in the name of the comet. And it was first observed on the 9th of January 2023. The Atlas part of the name is the Asteroid Terrestrial Impact Last Alert System. That's what Atlas is, and that's a NASA-run observatory, I think, in South Africa, and that was observed on the 22nd of Feb by that observatory, so hence the dual name, Tsuchinshan Atlas. Next up, we've got a photo by Nerida Langcake with a smartphone, S Note 20 Ultra, handheld shot, and you can see 5 a.m. early in the morning. It's still an early morning object and quite visible there, even with a smartphone photograph. And here we've got a bit of a time lapse by Chris Black taken on the 30th of the 9th. And the other thing you'll notice is all of the morning shots, all of the morning images of the comet have got it facing angled, coming down from top left to the horizon. And then when it switches over and becomes an evening object, it flips and it's visible with the tail on the other side going from top right down to the horizon. So the C2023A3 part of the name is a minor planet designation from the Minor Planet Center, which is a branch of the International Astronomical Union. So that's where these funny names, C2023A3, come from. So thanks, Chris Black, for that one. Another great shot by Mark Hillen from Flinders. So a single image just with a digital camera, SLR camera, 15-second exposure, and again, you can really see that magnificent tail there. So with the name of it, the C part of the name at the front, you would think stands for comet, but it doesn't. There are 4 different types of designation that you can have at the start of the comet's name. You can have C, D, P, or X. C does not stand for comet, but it designates that the comet has an open trajectory around the Sun, so it's not likely to ever return. So it's not necessarily a closed orbit. This one, they're not sure if it will return or not, and if it will return, it'll be hundreds of, maybe 50 to 100,000 years from now. So the C designates that it's an open orbit. The other designations, P is for periodic comets, so ones that we see regularly, like Halley's Comet. D is for comets that are only observed once, and X is for comets which are of unknown orbit. So not many comets these days have an X designation because we're pretty good at determining their orbits these days. And one of the most famous ones with a D designation, you might remember Schumacher-Levy 9. That was only observed once because it smacked into Jupiter, and that was in 1994. Okay, what have we got here? We've got Greg. Greg's got quite a few photos spread out throughout the period that it was visible, and this one he's got from the Chelsea wetlands with his Pentax and a 50mm lens on the 3rd of October. So what have we got? The conjunction of the Sun, the conjunction between the comet, the Earth, and the Sun was on the 4th of October. Or between the 4th and 5th, it was around about that sort of time. This one was on the 3rd of October, just before conjunction. Then soon after that, the comet wasn't visible for a little while because it was directly between us and the Sun. At its closest approach to Earth was on the 12th of October, and it was came within 0.47 astronomical units of the Earth, so halfway between the Earth and the Sun. What do we got? Okay, on the, what do we got here? Another one by Greg on the 20th of October, taken with a tracking mount. So it's, the reason it's on a bit of an angle there, you can see sort of the horizon on a bit of an angle in the corner. That's on Greg's tracking mount, so he's tracking the comet and getting a nice photo of it there. Oh, the other thing is, on about the 14th of October, and you may have seen, I can't really see it in any members' photos, but on the 14th of October, the Earth crossed between crossed the orbital plane of the comet. So some of the photos that you would have seen taken around that time had what's called an anti-tail, and that is a tail that seemed to be coming out in front of the comet. I haven't picked it up in any of the member images though, but what that is caused by is the comet's tail, or the debris left by the comet, and because we're passing within the plane, we're seeing the debris that the comet left coming around the sun, and then we're seeing it as it's going around again, and we're looking at it in the same plane. So there was an anti-tail that was visible that was coming out in front of the comet for a little while as well, that you might have picked up on some photos too. Okay, we've got a sea star photo here from Kelly Clitheroe from Clifton Springs on the Bellarine Peninsula, taken on, when was this one? 20th of October. Now with the comet names, okay, the C we said was designated the orbit of the comet, and then we've got the naming of it there. The 2023 is obviously the year that it was first sighted. It was first sighted in early January 2023. The A3 is also a timestamp, so the year is broken down into 24 parts for comet designations. A is the first half of January, B is the second half of January, C is the first half of February, D is the second half of February, and so on. So that's what the letter means, and the number means it's the third comet that was discovered in that period. So there would have been two other comets that were discovered in early January, 2023 A1, 2023 A2. This one was the third one. So there you go. The mystery of comet names has just been unravelled for you. Another photo by Greg Walton here, taken from Chelsea. This one is tracked as well. Yep, a 10-second exposure. 25th, okay, 25th was a busy night because this is when we had the scouts over here that Peter mentioned earlier. So there was quite a few of us trying to get photos of it, and this is a really nice stacked image taken by Ben Claringbold out here at the Briars. This one was taken by me through the Meade refractor with my smartphone, and looks better on my computer actually, but that was a 30-second exposure with my phone, which I used the phone holder. We've got a phone holder down in the observatory, clamped that on, and the hardest bit about that was trying to line up the right lens on my phone with the eyepiece, but managed to get lucky and get that shot through the 127mm refractor. And that same night, Greg got this one with his camera, so he had his Pentax, he put that on the refractor and managed to get this shot here on the 25th of October as well. And Jamie got this one as well by handheld smartphone on the same night too. So, and that was from here as well. A couple nights later, I thought I really wanted to get a nice shot, and so I got back down here with my Astro camera and whacked it on the refractor again. I managed to get 11 frames before the clouds came over, and stacked them up and got that result. Not too bad, but Guido got this one from Nil. So this was during the star party at Nil through his ZS-73 telescope and his Astro camera. And you can see, as compared this to the previous photos before it passed between us and the sun, the tail really is getting shorter and shorter, the comet's getting fainter and fainter, and you do really need a telescope to view it, whereas before you were getting some really nice shots just with a wide-angle camera lens. David Rolfe got this one, a single luminance exposure with his setup, with his William Optics 71 telescope and his 2600mm camera, monochrome camera. So luminance exposure means there's no filter on it, it's just a black and white photo. Again from Neil on the 3rd of November, Greg got this photo with his refractor as well. He had a 6-inch refractor set up at the star party. We were getting some really nice views of that. And he also got this one here, a stacked image through that same refractor as well, 6 30-second shots. And that was on the 4th of November. So Comet well and truly getting fainter and fainter, and our last image by Sylvie Grandit, unfiltered, and we're saying goodbye to the comet. So well done, Sylvie. That was a pretty challenging shot from what I read. You had spiders and cyclones and things are going on trying to get that photo, so well done. The challenge is always to get the shot, so well done everybody who got photos. Next one is Space People. So this one will run until the January meeting. We've got no meeting in December. We're talking about constellations, stars, objects depicting people and characters. Example, we've got Orion coming up now, interesting character. Gemini twins are coming up late, but they'll be coming up a bit early and early as we go through late December, early January. Gabriella Mistral Nebula in Carina, and I never figured out why it was called Gabriella Mistral, and then I saw a photo of Gabriella Mistral on Wikipedia and it made sense. So if you look at the nebula and then you compare a photo of the lady herself, you sort of think, yeah, okay, I get it. Planets, obviously, gods, people, same sort of thing, characters. Thor's helmet, which is a Wolf-Rayet star in Canis Major, I think. The Witch Head Nebula, which is a photo I managed to take last year there. Canopus, the navigator, if you want to take a photo of a bright star in the background. Canopus, the navigator or pilot of the Argo Navis, is another option too. Or objects within these constellations, larger constellations, whatever you can think of that is related to a person or depicts a person or a character in the sky. That's our next challenge. So get your shots and send them in to me by whatever means you like, and there you go. Any questions? No?
Chris, you said there was 3 comets discovered in the first week of January.
First half of January, yep.
So, yeah. Is that pretty common? Like 3 seems like a lot.
Well, it is, because we've had comets named up to number 5, 6, 7. Sometimes there's more discovered, sometimes there's less. It's
just 3 in that 2 weeks?
Yeah. Wow. Yeah, but you do have comet. If you look at comet names, going back, you'll see, you'll start to notice now. A3, well, not Z. Z doesn't get used. I doesn't get used. Okay, Z and I don't get used to designate comet dates because I looks too much like a 1, so that'll be too confusing, and we don't need Z because we only need 24 letters. But yeah, you'll see, B5, H11, H3, whatever. You'll start to notice it, and then you'll see that there's actually quite a few of these things that get spotted. Yeah. Anyone else? Excellent. Thank you, Peter.
Welcome to Sky for the Month for November, December, and January, because we won't have a meeting in December. So let's have a look at the solar system. Pretty much the same view that Chris just showed. This is for the 21st of November until the 13th of January. So I've sped it up a bit so we will be able to see how the inner planets travel during that time. And as you can see, we're currently up here in relation to the Sun and the other inner planets. Mars is up here. You can't see that at the moment there. And so everything that's in this direction here would be a morning object, right? Because that's kind of looking towards the sunrise, and anything in this direction would be an evening object. So if we start to fast forward here, and we go through those 2 months, you can see Mercury will pass between us and the Sun during that time, and we are catching up with Mars over here. Until we reach the opposition in mid-January, right, when Mars is exactly opposite from the Sun. And yeah, Venus still stays within the evening sky for that entire time. We can also zoom out into the outer solar system. We can see we're pretty close to Jupiter now as well. Saturn is still a nice evening object for now, and Neptune and Uranus somewhere in between. We'll see that in the overview later. So let's have a look at the night sky on the 1st of December. So just before sunset, we can see Mercury pretty close to the sun now. We had some really nice views of Mercury at nil a month ago, but it's now getting pretty close to the sun again. Sunset now is around 8:30 p.m. and we'll see Venus and Saturn in the sky there right after sunset. So Mercury is at its inferior conjunction, so between us and the sun on the 6th of December. So there's going to be a while where we can't see it at all. Venus remains a really bright evening object for the next couple of months. And then we have Saturn, now well past opposition, but very high in the sky, so we can easily see it all night, right after sunset. And Neptune ends its retrograde motion on the 8th of December. So very close to Saturn there in the sky. So this is around 9 p.m. now. So if we then go towards midnight, this is around 10 p.m. So the main stars in the sky in early December would be Canopus, Arcana, and Fomalhaut there in the middle, and we now very clearly have Orion and Sirius in the sky again at reasonable time. So when you come out afterwards, hopefully we get a bit of clear sky. Orion should be visible from around 10 p.m. now, or 9:30, 10 p.m. So let's have a look at the other planets, in particular Jupiter and Mars. So Jupiter now also rising well before midnight, and Mars rising a bit earlier as well, coming up there. Uranus now also past opposition. Jupiter coming towards opposition on the 8th of December, and I'll have a few more slides on that in a minute. And Mars now rising around 10 p.m., a little bit later, and heading towards opposition on the 16th, and I also have a few more slides about that. But I thought we could have a look, let's just wait for sunrise and have a look at the moon. So sunrise now is around 10 to 6 on the 1st of December. And we have a new moon on the 1st of December, a full moon on the 15th, another new moon on the 31st of December, and then the next full moon in January on the 14th. I thought I show you a bit of a time lapse of the night sky just between now and mid-January to see kind of how that changes over that time. So every step here is 1 day. So we can see that especially, and this is around 10:30 p.m. So we can see that Orion will be quite a bit higher in the sky every night now, between now and mid-January. And you can see the Southern Cross here pretty low on the horizon still around that time. All right, so just to kind of orient yourself in the night skies, it's going to be mainly Orion in the east that'll help with that. And if you have a nice horizon in the south, you will be able to see the Southern Cross and the 2 pointers there low in the south. Okay, this is a comparison of the apparent sizes of the planets on the 1st of December. But I think what's probably more interesting is to look at Mars and Jupiter in particular, because both of those are heading towards opposition now in the next few months. So the first one is Mars. So I wanted to show you just a comparison of the orbits of Mars and the Earth. This is the opposition of Mars in 2003, and I'll show you in a minute why that was an interesting year. So you can see Earth and Mars here, and Mars is exactly on the opposite side from the sun. So basically at midnight it'll be as high in the sky as possible, and also it'll be at its closest point in its orbit with Earth, so we'll get a nice view of the planet. So this was 2003, but what you can notice is that Mars has a pretty elliptical orbit, right? So the orbit of Earth is much more circular, but Mars actually sometimes is a lot closer to the sun than at other times in its orbit. And so at the moment, the next opposition that will happen in January 2025, this is where we are in our orbits, right? So Mars is up here and the Earth is around here. And so you can see the distance between the two planets now is a lot further, right? Which means that Mars will appear a lot smaller in its orbit. And the other effect of the different orbits is that the orbital planes are inclined to each other. So we don't always see it kind of at the same altitude in the sky. So this is a quick chart of the maximum altitude at opposition. So for example, in 2003, it was at more than 60 degrees altitude at opposition. Next year, it'll be at 25 degrees. So not ideal for viewing, right? And then we can actually look at the different sizes of the planet because we're much further away. It'll also be pretty small. So unfortunately, it's not going to be a great opposition for viewing Mars. And the next few years after that, or the next few oppositions, because it's every 2 years roughly that we're in that position, the next few oppositions won't be any better. So here's a chart of the different sizes over the years from, I think, 2001 all the way to 2029. And this is going to be the next one. So probably rather boring one. And I thought I'd just plot the same thing for Jupiter. So it also, because of the orbital planes, we also have different altitudes at opposition at night. So you can see that the 2020 opposition, we had it really nice and high in the sky, around over 70 degrees, whereas the 2025 one here will be only around 30 degrees or so. So you can notice Jupiter's already up in the sky now around like 10 p.m. or so, but you will see that it'll stay pretty low over the horizon. So it again won't be that great an opportunity. But with Jupiter, because the orbit is so much further out, actually it's not traveling that much within one Earth year, right? So the difference in size isn't actually that great, right? So these are again oppositions from, I think, the last 15 years or so. And you can see that the size is a bit different at opposition, but it doesn't make that much of a difference compared to Mars. All right, moving on to comets. This was the only one that I could still find that's still in the sky at the moment, if you can find it. But I think we just saw the goodbye pictures that Sylvie took, so it's not going to be that interesting. Should be basically setting just after sunset now, and then basically becoming a daylight object and fading to magnitude 11 and lower. So yeah, that's the last time I'll mention this one, I guess. And then meteor showers. I'm not even sure. Like the first one was mentioned in the almanac. I don't think it's that interesting for observing from around here. The Geminids are going to happen between the 4th and the 20th of December, peaking around the 14th, 15th. And they can be bright, and there can be many of them, but we will basically have the full moon around the time of the peak. So unfortunately, again, probably not that interesting to view. We tried to see whether any of the recent meteor showers had been captured by our all-sky camera. I just had a look earlier, but basically all of them were around the full moon, so the camera just didn't pick anything up as far as I can see. And I think that's all I had. So the sources, as always, were the Stellarium app, the NASA Eyes on the Solar System website, and the Astronomy 2024 Almanac. Any questions?
Did anybody actually see any of the Leonids?
I think so. The Leonids was one of the ones that I tried to find on the all-sky camera. So I didn't see anything on the camera, and I didn't see anything myself. Yeah.
When will Mars be closest again to going from that chart to show?
So this. Oh, actually, I didn't check. Probably, yeah. No. You're probably right. Right? Because it should be roughly cyclic. So yeah, probably another 10 years or so. Yeah. Yeah. So at least for the next few years, it'll be pretty low and pretty small. Yeah. All right. Thanks.
Tonight's feature, which goes for about an hour, is all about the weirdest stars in the universe, given by Assistant Professor Emily Levesque from Seattle, University of Washington. And some of these stars you'll actually recognise the names in the sky, but you may not realise why they're a bit weird. This was actually hosted by the Perimeter Institute, and we've given their talks before in the past as well. They do an excellent job. Canadian Institute in Ontario. If you need to get up and grab a cup of coffee or go to the toilet or something like that, feel free to do so. Don't feel inhibited, and come and go as you wish. So this goes for about an hour. Then we'll have a few shorter science videos afterwards before closing.
Dr. Levesque is an assistant professor of astronomy at the University of Washington in Seattle. She received her bachelor's degree in physics from MIT and completed her PhD in astronomy at the University of Hawaii, and was both an Einstein and a Hubble postdoctoral fellow at the University of Colorado. Emily is a rising star in astronomy research. Her accolades include a 2017 Alfred P. Sloan Fellowship and a 2014 Ann Jump Cannon Research Prize from the American Astronomical Society. Dr. Levesque's research focus is on massive stellar astrophysics and the use of massive stars as cosmological tools. Tonight, she will discuss some of the strangest stellar phenomena in our universe and how these weird stars serve as a common thread for exploring our universe's history, evolution, and extremes. Ladies and gentlemen, please welcome Dr. Emily Levesque.
Well, hello and welcome to tonight's lecture. I'm extremely excited to be here and so happy to be sharing these very weird stars with all of you. I always like to start by putting up some pictures of some of the weirdest stars in the universe. So every object that you see on the screen right now represents some sort of bizarre or unexplained or particularly puzzling type of star, something that has surprised or confused at times astronomers. As I go through the talk and I look at things that are particularly weird or surprising, I'll be marking them with these little exclamation points. I can also promise you that by the time we get to the end of this talk, you'll be able to name every single thing on this screen. You'll be able to explain what it is, at least as well as astronomers can explain them, and you'll recognize all of them if you ever happen to come across them again. So to start off talking about weird stars, we need to establish what is considered normal for an object like a star. And to do that, I actually need to start with a diagram. So this is a very common diagram used in astronomy. It's called the Hertzsprung-Russell diagram. What we're doing here is plotting temperature on the x-axis, going from very hot on the left to very cold on the right, and plotting brightness on the y-axis, going from dim at the bottom to very bright at the top. What we can do with this is drop the collection of normal stars that we know about onto the diagram and see where they land. You can kind of see that there are clear spots where normal stars tend to hang out. I'll fill this in with a slightly more detailed version of the illustration, and you may recognize the names of some of the stars on the plot. I always like to point out where our sun is. So our sun is right in the thick of things, and our sun is really a kind of depressingly normal and unremarkable type of star. So the main thing that we use this diagram for in astronomy is explaining how stars evolve. And this is something a lot of people don't necessarily realize stars do. They're born, they age and evolve with time and change, and then eventually they die. And you can plot out how a star is going to live and die by following its path on the Hertzsprung-Russell diagram over the course of its life. You can see the sun, you can see that sort of diagonal of very normal-looking stars. The stars that I'm interested in, and the weird stars that we'll be focusing on tonight, are at the very top of this diagram. So these are the supergiants. These are massive stars. They're stars that are at least 8 times the mass of our sun or more. And I want to start by taking a short tour through these stars on the Hertzsprung-Russell diagram and looking at how they evolve. I like to use examples of stars that you can find in your own night sky. So to begin with, I want to look at Spica. Spica is a star in the constellation Virgo. It's an amazing example of a blue supergiant. So this is a massive star in the first phase of its life. It's fusing hydrogen into helium in its core. It's very hot. It's about 22,000 degrees Celsius. That's much hotter than our sun. Our sun is 5,500 degrees Celsius. It's about 7 times the mass of our sun, and it's about 10 times the mass of our sun and about 7 times the size. A star like Spica will stay in this part of the HR diagram for maybe 10 million years, fusing hydrogen into helium. Eventually, the star will run out of hydrogen, and it needs to try fusing something else. So it switches from fusing hydrogen to helium. When that happens, the stars actually go streaking across the top of this diagram from left to right very quickly. After 10 million years fusing hydrogen, they cross from the hot to the cool side of the plot in about 100,000 years. Along the way, though, they make a brief pit stop when we would consider them yellow supergiants. And we actually have an amazing example of a yellow supergiant that we all know really well. Our North Star, Polaris, is a yellow supergiant. This is actually pretty surprising because stars like this are rare since their lifetimes are so short. So it's pretty cool that our North Star is this relatively rare type of massive star. Once these stars have completed their trip across the diagram, they wind up as something like this. This is Betelgeuse. It's in the constellation Orion, a constellation that I'm sure many of you are familiar with. It's very easy to find in the night sky if you look for those 3 stars that make up his belt. And you can see Betelgeuse as his left shoulder. It's a very bright star that is very obviously red. Betelgeuse is an excellent example of a red supergiant, which are one of my research specialties and a particularly fascinating type of massive star. What's interesting about a star like Betelgeuse is that as it has cooled off and moved across the Hertzsprung-Russell diagram, it's also gotten enormously big. This star was born with maybe 15 or 20 times as much mass as the sun, but it's 900 times the sun's size. So I want to try and put that into context. This is the orbit of the Earth. That one dot in the center, it shows up as a couple pixels on the projector, is our sun. If we back up a little bit, we lose sight of the sun, but you can see the size of Earth's orbit relative to things like Jupiter's orbit and Saturn's orbit. If we were to put Betelgeuse where our sun is, it would stretch out to well past the orbit of Mars. It would begin approaching the size of Jupiter's orbit. So this is incredibly big and in its own right makes the star a bit weird. There's a couple funny consequences of a star being this big and this cool, and I want to again try and compare it to the sun. So this is an image of our sun, and if you were to zoom in on it very close, you would see things like this happening on the surface of the sun. These are called granules. What we're seeing are the very tips of a convective layer in the top, near the surface of the sun. What we're seeing is gas that starts out hot, rises to near the surface of the sun, cools off, and then falls back. It's not unlike watching bubbles boil in a pot of water. So on the scale of the sun, these are tiny. But stars like red supergiants do this too, and the effect is a good deal more dramatic. So if I put the sun away, it is now a single pixel on the screen, but I promise you it's still there. We can, to scale, compare the sun, there it is, to Betelgeuse. This is what those same little cells look like on the surface of Betelgeuse. The whole star is boiling and roiling and changing very dramatically when you look at how bright it is. This is a consequence of how large and how cold it is. And this is a normal red supergiant. This is very typical for stars like this. So it starts to establish why these stars are as interesting as they are. We went through the Hertzsprung-Russell diagram and we followed stars starting as hydrogen-fusing blue supergiants, crossing the diagram to briefly become yellow supergiants, and ending up as helium-fusing red supergiants. We can actually draw a line to represent the journey that we just followed. This is how a 15 times the mass of the sun star would move during the course of its lifetime on the Hertzsprung-Russell diagram. We call something like this an evolutionary track, and it's a great way to quickly and at a glance look at how a star is going to behave during its lifetime. This is actually a really great tool for studying theories of how stars evolve. This is an evolutionary track for a 15 solar mass star, but we can take a bunch of evolutionary tracks like that and draw them on a Hertzsprung-Russell diagram. We can look at what a 12 solar mass star will do, what a 20 solar mass, what a 40 solar mass star will do, and get a good sense of what normal massive star evolution looks like. So there's something you might notice on this diagram, and it has to do with how cold the stars get. Every one of these evolutionary tracks was computed using our understanding of stellar physics, and every single one seems to stop at about the same temperature. Every one is not really getting any colder than about 3,000 degrees Celsius or so. To the right is this region where we don't think stars should be able to stably exist. Everything we know about stellar physics suggests that stars should not sit in this part of the diagram. Now, I mentioned red supergiants, and I mentioned that they're incredibly cold. We think that those stars should sit right at the edge of these evolutionary tracks, but for a long time, if we observed red supergiants, if we measured their temperature and we measured their brightness, and we tried to put them on this diagram, those stars would land here, in exactly the place that they don't belong. This bothered us for a very long time. We were trying to understand what was wrong with our stellar physics, what was wrong with our theory of how these stars evolved that could explain this really bad match between red supergiants and the predictions of evolutionary tracks. What finally clued us in was when we started looking at where the temperatures of those stars were coming from, and when we developed a very good way to measure those temperatures more accurately than we had before. The way that we'll do this is to take light from a red supergiant and sort it out into something called a spectrum. So in a spectrum, you observe light from an object, and you sort it out according to its wavelength. So the very bluest light will be on the left side of the diagram, and the very reddest light will be on the right. The brightness is still represented on the y-axis, so you can tell at a glance that this is sort of a spectrum of a reddish star because we're seeing more red light than blue. This is a cartoon version of what a red supergiant spectrum would look like. An actual red supergiant spectrum looks like this. It's a lot messier, and something you notice right away is that there are these strange sort of bites taken out of the spectrum. There's these little dips that show up periodically as we go from blue to red. All of those dips represent light that has been taken out of the spectrum on its way to us. That's light that's been absorbed by something in the atmosphere of the red supergiant. In this case, that is light being absorbed by titanium oxide molecules. These stars are so cold that molecules are able to form in their atmospheres. It makes the spectrum look interesting, and as it turns out, it's also a really good tool for measuring temperatures. If you look at a simulated spectrum of a red supergiant and you cool the star off, at 4,000 Kelvin, you really don't see that many titanium oxide absorption signs at all. As you cool the star off, they suddenly appear, and they get stronger very quickly. What it means is that we can use those dips in the spectrum as tools for measuring temperature. If we observe a star and we see very strong dips, that means the star is very cold. If we see very small ones, it means it's relatively warm. We decided to check this out as a means of maybe improving our temperatures for red supergiants and maybe fixing that problem that we'd come across on the Hertzsprung-Russell diagram. This was actually my very first research project. As an astronomy student, I worked on this after my sophomore year at MIT. I got to go to Kitt Peak National Observatory in southern Arizona. I had my very first observing run. You can't tell from this image, but I'm unbelievably excited because they're letting me open the dome of the 2.1 meter telescope, and I'm gazing up going, ha. We had 5 perfectly clear nights. This was wonderful observers beginners-like, and this has never happened to me again. And we got spectra of 75 red supergiants in the Milky Way. We used that technique, looking at those titanium oxide bites in the spectrum, to measure their temperatures, and then we replotted them on this same diagram. So when we remade this with our temperatures, the red supergiants moved from here to here. We had completely fixed the problem. This was enough, that little shift on the diagram was enough to get us unbelievably excited. Yes, we've done exactly what we set out to do. Physics isn't wrong. These stars work. This is excellent. Let's write the paper. And along the way, we wound up discovering something very cool, literally, and entirely by accident. So on this plot, we've depicted each star's temperature and each star's luminosity. And there's a very handy equation. This is the only equation that I use in the talk, but it's a very important one to have. There's an equation in astronomy that relates how luminous a star is and how cold or hot it is to how big it is. And I can walk through what everything in this equation means. L stands for the luminosity, how bright the star is. Well, we already knew that. We know how much 4 is. We know how much pi is, that's just a constant. And we know how much sigma is, that's another constant. We had measured temperatures, so now all that was left was the radius. We had everything at hand, so we figured, why not? This is just an algebra problem. If we move radius to the other side of the equation, take the square root of everything, we've measured radius. So we went ahead and calculated the size of every star in our list, and we put everything in a big table, and we started moving on to try and publish the paper. It took one of our research collaborators looking at this table and going, hang on, I don't know if you've noticed one of the numbers in this list, but it's astonishing. This is the largest radius I've ever seen measured. We might have discovered the largest stars in the universe. We went back and did everything again. We checked everything twice. But it turned out it was true. As part of this project, we had, by surprise, discovered the very largest stars that anyone had ever seen. So for comparison, I showed you where Betelgeuse sat if we put it where the sun was and compared it to the orbits of the planets. This is the size of our new record holder, a star named KY Cygni. It reaches out well past Jupiter. It starts approaching the size of Saturn's orbit. So this on its own, hitting this extreme of stellar evolution, most definitely marks KY Cygni as a weird type of star. So we've gone through how stars move on the Hertzsprung-Russell diagram. We've talked about these cold red supergiants fusing helium in their cores and how they can get fascinatingly big. But eventually, those stars also run out of things to fuse in their cores. Does anybody know what happens when we get to that point? Supernova. Yes. So to understand why a supernova happens, it helps to look at what's going on inside the star right before the supernova. Massive stars started out their lives fusing hydrogen into helium, then they moved on and fused helium into carbon, and they progressed fusing heavier and heavier elements. By the time they reached the ends of their lives, if you were to slice one of these stars in half, it would look like the inside of an onion, with layers of every single element that it's been using for fusion or as the product of fusion inside. This star gets into trouble when it starts to try and fuse iron. This fusion happening in the core of the star serves a very important purpose. It helps the star maintain this very delicate balancing act between the inward press of gravity and the outward press of that fusion. As long as that balance is maintained, the star is going to be alive and it's going to be just fine. Fusing iron disrupts this process because fusing something like hydrogen or helium or carbon produces energy. If you try to fuse iron, you need energy. So at this point, that delicate balancing act has been disrupted. And I have an animation of what happens once we do that. So in this animation, we're zooming into the center of a red supergiant, and you'll see the colors in the center of the star change to represent different fusion processes that are occurring. As we switch from fusing hydrogen to fusing helium, as we switch from fusing helium to fusing something like carbon, you'll see the color change again. And the star will progress through different fusion sources until it attempts to fuse iron. This goes terribly for it. And then in less than a second, that iron core implodes. All of the material in the outer layers of the star tumbles down onto that imploded core and then bounces back out. And that rebound bounce gives us this unbelievable explosion that we see as a core collapse supernova. So this is an incredibly dramatic death for a star, and supernovae are amazingly bright. This picture here is from a cave dwelling in Chaco Canyon, New Mexico. It shows a few illustrations on the rock. You can see what looks to be a daytime moon. You can see a person's hand. And then you see this. This, we believe, is a depiction of supernova 1054. This supernova went off on July 4th, 1054, and was in our own galaxy. It was very nearby. It was so bright that you could see it during the daytime sky for 2 weeks. We have historical records of it from Arabic astronomers, from Chinese astronomers. They called it a guest star because it appeared, stayed for a little while, and then left. This actually left behind what we now know as the Crab Nebula. The Crab Nebula is the remnant of that 1054 supernova, all of that material that got blasted off of the star now dissipating into interstellar space and giving us what we call a supernova remnant. That was an unbelievably dramatic supernova, and it was extremely bright in part because it was so nearby. It was in our own Milky Way. We had a supernova like this in 1054. There was a supernova in 1572, one in 1604, and we haven't had one since. Every modern supernova that we've studied has been in another galaxy, and it's a little bit less of a fireworks show. So this is an image of M51. This is the Whirlpool galaxy, and it's an image from January of 2005. In July of 2005, a supernova went off in M51, and there's actually a really great image of that supernova happening. Did you see it? Such a dramatic explosion. Let me do it again. Yep. Usually when I turn it off, then I hear this, oh. So that was the dramatic supernova, 2005 CS. We name supernovae based on the year that they happen and how many we've seen in that year. So this supernova happened in 2005. We started with supernova A, B, C, D, and went through the lettering. So these supernovae are fairly common. You can tell if we got all the way down to CS, there's quite a lot of them. This was a pretty bright and still pretty dramatic by astronomy standards supernova. We cataloged it, and we watched it do what a normal supernova does. It got incredibly bright, and then over the course of about a year, it faded away. This is what an exploding star should do. Sometimes we see something a little bit different. So this is the beautiful galaxy, NGC 7649, and by galaxy I mean the little fuzzball in the middle of the picture. As we get farther away, the photos get a little bit less dramatic. This galaxy hosted a supernova, we thought, in 2009. This little bright thing appeared. We identified it and immediately said, hey, we found another supernova. This is supernova 2009 IP. It got that name. We saw this thing get very bright. We watched it fade away. And we thought, well, perfect, another supernova doing its supernova thing. And then it reappeared in 2010. It reappeared again in 2011. In 2012, we finally saw a very dramatic eruption from this star, and we think that this star might now be dead, although people are still keeping an eye on it and looking here just in case. This was an example of a star that, from our perspective, was just pretending to explode. What supernova 2009 IP actually is an example of something called a luminous blue variable. We tend to name things really literally in astronomy. We talk about, red supergiants, or our telescopes are named fabulous things like the Very Large Telescope. So luminous blue variable is very literally what these stars are. They're luminous, they're incredibly bright. They're blue, which means a lot of the time they're very hot. And the key thing is that they are variable, so they change with time. A star like the one that produced supernova 2009 IP is variable because it's flinging off enormous amounts of mass that appear to us as something very akin to a stellar explosion. What we're seeing instead is an eruption, and we still have a very limited understanding of what causes eruptions like that. We have an amazing example of this in our own Milky Way. This is a photo of Eta Carina. It's about 7,500 light years away. And if you look at that image, it looks like you're looking at something that exploded. It looks like the violent post-death of a star. What we're instead seeing is material that got flung off of the star during an eruption in 1843. When that eruption happened, Eta Carina got so bright that it was actually the second brightest star in the night sky for a few days. It's faded away since then, but incredibly, the star is still in there. The star survived this explosion, and what we're left with is this very fascinating material from that eruption that we're still studying in the hopes of maybe trying to explain what luminous blue variables are up to. So I want to go back to the Crab Nebula, to this remnant of a supernova. I explained how a supernova happens. You have that collapsing core, material tumbling down after it, and then rebounding and giving us this explosion. The exploded material winds up giving us something like a supernova remnant, like the Crab Nebula, but there's actually something else in here that's worth highlighting. At the heart of the Crab Nebula is something called a neutron star. So a neutron star is what is left over when the core of a massive star collapses. Neutron stars are absolutely fascinating. They aren't working like the normal stars that I've described, these stars that have to fuse something in their cores to maintain a balancing act with gravity. These stars are actually supported by principles of quantum physics. They're supported by something called neutron degeneracy pressure, hence why they're called neutron stars. And the basic principle behind this is that neutrons that are very similar to one another, they have similar quantum properties, they occupy a similar state, cannot be squeezed too close together. They will literally resist this to the extent that they're able to support themselves against gravitational collapse. Neutron stars are unbelievably dense and unbelievably small. One of these stars is the size of the city of Waterloo. But if you took just 1 teaspoon of it, it would weigh more than a mountain. We're talking about a very extreme scenario in terms of the matter in this star. You also sometimes see something interesting from a neutron star. This is an artist's rendition, and you'll notice those lines sort of poking out of the star in opposite directions. Those are showing the magnetic field lines of the star and illustrating that some neutron stars can be what we call a pulsar. In some cases, these stars will emit light out of their magnetic poles. Now, we know on Earth that our geographical pole, the actual pole that the Earth rotates around, is different than our magnetic poles. In an extreme case like our neutron star, what you'll get is a beam of light flinging around as the star rotates and sort of causing a flash as it goes by. The best analogy that I've been able to find is looking at something like an emergency light on top of a fire truck or a police car. Those are 2 beams of light pointing out in opposite directions, and as you spin it, it appears as though something is flashing. That flash is what we detect when we see something like this, a pulsar. Pulsars were actually discovered in a pretty interesting manner. They were detected by a woman named Jocelyn Bell Burnell in the 1960s in the radio. She actually detected first 1 and then 2 and eventually got up to 4 objects like this. Their pulsations were perfect. It sounded like you were almost hearing a heartbeat from these stars. They temporarily nicknamed the objects LGM 1, 2, 3, and 4. And LGM was an abbreviation for little green men. And they were mostly kidding. But it was a sort of tongue-in-cheek nod to the fact that this was such a perfect and regular signal that maybe somewhere little green men were making this. It turned out that wasn't the case at all, and instead it could be explained by a neutron star that was specifically emitting this light and detectable as a pulsar. So I've talked about these neutron stars that can form when the core of a massive star collapses. If that collapse goes 1 step further, if we have more mass in the core, or if that neutron star gains mass with time, we instead produce something else. We produce a black hole. I apologize for the artist rendition. You understand. These stars will produce black holes as part of their deaths. Now, the black holes themselves are utterly fascinating. But what I'm particularly interested in are a subset of stars that actually do something very strange when they die and produce black holes. These stars produce something that we know as gamma ray bursts, and I have an animation of what this looks like. This is a massive star, something like 40 or 50 times the mass of our sun. Now you'll notice it's blue, it's not red. The outer layers of this star have actually been ripped off over the course of its life, exposing some of the hot inner layers. When this star dies, its core collapses into a very rapidly rotating black hole. That black hole starts consuming the star and almost shattering the star from the inside out. And it ignites these unbelievably high energy jets of material, shooting out perpendicular to how that black hole is rotating. It consumes the star, collisions in those beams, produce the gamma rays that we detect here on Earth, and eventually the death of the star ends with the same sort of supernova that we talked about before. So that whole video took about 15 or 20 seconds. That was in real time. A 40 solar mass star will actually die and produce a gamma ray burst in a comparable amount of time. So this is an incredibly violent death for a star. It's incredibly weird, and that's an amazing timescale to work on for something that huge. Those flashes of gamma rays that we see from stars like this were actually discovered by accident. So these are the Vela satellites. It's a sketch of these satellites that were launched in the mid-1960s following the signing of the Nuclear Test Ban Treaty. So the job of the satellites was to orbit the Earth, monitor the planet, and look for signs that somebody was violating the treaty and performing a nuclear test, which would have shown up as a flash of gamma rays. And the satellites worked great, and they detected many flashes of gamma rays. And fortunately for world peace, none of them were coming from Earth. Instead, they were coming from all over the sky. It took us a long time to try and explain what we were actually seeing when we saw these gamma rays. What we finally determined was that we were seeing flashes of these dying stars from other galaxies. We've now put up dedicated telescopes whose job it is to look for gamma ray bursts and to tell us when one has happened as quickly as possible so we can try and study them. So this is the SWIFT spacecraft. It's a tailored telescope for detecting these sorts of gamma ray flashes. That flat panel that you see on the front is a gamma ray detector. And then under what looks like a baseball cap, but is actually a sun shield, are X-ray and ultraviolet and optical telescopes that try to observe these objects as fast as possible. What SWIFT will do is it will sit there orbiting the Earth, waiting for a gamma ray burst to go off somewhere in its field of vision. It'll spot a gamma ray burst out the corner of its eye, go, oh my God, turn, and start taking data on the gamma ray burst as quickly as possible. When it does that, it sends a notification down to Earth to astronomers saying a gamma ray burst has just happened. Remember, that flash of gamma rays lasts 20 seconds. We see light from these events in other wavelengths, but they still don't last very long. So there's a great reason to try and go after these events and study them as quickly as possible. So this gets into a type of astronomy called time domain astronomy. I love this discipline. It focuses on trying to study things that are very fleeting and very quick. It's the closest, I think, that we get to sort of movie-style astronomy. So I want to do a quick comparison between how a movie might depict time domain astronomy, detecting a gamma ray burst and having to chase it very quickly, versus how it actually happens. I would contend that I think the way that we actually study these could be more interesting than a Hollywood film. But in Hollywood, if you detected a gamma ray burst and you wanted to do something very quickly with it, the detection would be announced by the science siren going off. For some reason, this is always a very public and very easy thing to do. Astronomers would get this notification that something exciting had happened. They would run to their telescopes, wearing lab coats for inexplicable reasons. They would look through the telescopes with their eyes, and they would naturally see something like this. They would see perfect, beautiful, colorful data. They would realize that something that they had observed would help them to save the world. They would dash off to talk to aliens or stop an asteroid or find a new home to live on. And that tends to be how the movie goes. The reality is a little bit different, but I think some of the things that we do are more fun. So in reality, a science siren does not go off when a gamma ray burst is detected. Instead, you get a notification on your phone. You will see a text alert or an email. There are astronomers who are signed up specifically to get notifications if something this exciting happens. Once that happens, the astronomer holding the phone gets to go, all right, we have now triggered something called a target of opportunity. There's something that's happened in the sky that we want to follow up as quickly as possible with the best telescopes possible. They will have access to something like the Keck 10-meter telescopes, which are on the summit of Mauna Kea in Hawaii. They will contact these telescopes and say, you have to stop whatever you're doing. I'm sorry, astronomer who is doing their own science. You have to stop whatever you're doing and take a little bit of time to observe this object in the sky very quickly before our chance goes away. I think that these telescopes are unarguably cooler than the lab coat and eye version that you might see in a cartoon or a movie. To give you a scale of what a 10-meter telescope looks like, that's a about 6-foot-tall person standing in front of one of the two Keck telescope domes. So you'll call in, you'll trigger this observation, and you hope that the night looks like this. You hope that it's beautiful and clear, and you can get amazing data of whatever you're wanting to observe. The night might look like this. This is an actual photo that I took when I was trying to observe at Keck, and when you can't see the building that's like 30 feet away, your odds of detecting something in deep space are getting really bad. You can't even open a telescope when it's this crummy out. It's unsafe for the telescope and the instruments. Hopefully the weather is clear, you take observations and you get gorgeous data. This is beautiful data, and by the way, that's the thing you're looking at. The bright object up top is something else in the way. There's a lot that has to be done to data before it can be finalized. You have to account for things like the background glow of the sky, electronic noise from the instruments on the telescope. So there's a lot of effort that goes into eventually turning this into science. Once you have a discovery, you don't run off and call the president and save the world. You wind up posting your results in some form of scientific publication. Something might be pretty quick. You might just want to say, oh, we got a little bit of data on a gamma ray burst or on a supernova, so you'll put it on something like the Gamma Ray Burst Circulars Network on the upper left, or the Astronomer's Telegram, which is now a website, on the lower right. You might write a research paper for something like the Astrophysical Journal. You'll put those papers on a public paper repository. This is how we tend to spread our results around. We'll work on something, we'll analyze the data, we'll very carefully get to an end result, and then we spread it around to the community. Astronomers can sometimes still be amazingly fast at doing this, but it winds up being a much more controlled way to do the science, and it ensures that a lot of what we wind up seeing is both incredible and accurate. So I think my favorite recent example of target of opportunity and time domain astronomy was related to gravitational waves. And I'll start by briefly explaining what gravitational waves are. A lot of you probably recognize this animation. This animation came out when the first discovery of gravitational waves was announced in early 2016. They had detected gravitational waves from two black holes that were colliding. This animation was everywhere. It's excellent, but I like to use something a little bit different to understand what a gravitational wave actually is. So I want you to imagine that you're holding something like a slinky. And if you look at the slinky between your hands, there's at least two different ways that you can cause a wave. One is the obvious one. You take that slinky, you lift one end, and you watch the wave propagate from one end to the other. Gravitational waves aren't quite this. These are waves traveling through space-time. And what they're doing is something more like a compression wave. So if you took the slinky and shortened one hand and kicked off something like this, those compression waves travel through space-time and impact space-time along the way. And when a gravitational wave reaches Earth, we see something like this. So this is a wildly exaggerated effect, but you can see Earth sort of getting squeezed and then stretched as a gravitational wave propagates by and squeezes and stretches the space-time that Earth is in. We take advantage of that squeezing and stretching effect to detect gravitational waves. So this image is LIGO. This is the Laser Interferometry Gravitational Observatory in Hanford, Washington. There's 3 of these in the world. There's one in Washington, one in Louisiana, and one in Italy. And they're all specifically designed to detect gravitational waves. They consist of these 2 arms set at perfect right angles to one another. So each of those arms is exactly 4 kilometers long. There is a laser and a beam splitter in that central building. And what you can do on a normal day, on a day when there is not a gravitational wave, is fire a laser beam using the beam splitter down both of those arms at once. With each arm being exactly 4 kilometers long, the laser will travel the length of the arm, will be reflected off a mirror at the end, come back, and the 2 laser signals will have traveled the exact same distance in the exact same time. They'll cancel each other out, and you know, okay, there's no gravitational wave. Now imagine a gravitational wave actually happening and squeezing space-time and squeezing the detector. What I've just done is squeeze the picture so that the arm on the left is now a little bit shorter. Now, if you send lasers along those arms, they will arrive at slightly different times. The one on the left had a slightly shorter trip than the one on the right because of the effect of gravitational waves. We now see a signal, and we can confirm that we've detected a gravitational wave. This started out by detecting 2 colliding black holes, but last year, on August 17th, we detected something else. So these are 2 neutron stars, the same stars that I talked about before. They're orbiting one another in a very close binary. They're spiraling in, getting ready to collide. When they collide, they emit a very short flash of gamma rays, even shorter than the kind I talked about before, and they emit gravitational waves. We thought that this was going to happen for quite a long time, and On August 17th, a gravitational wave signal from 2 colliding neutron stars was detected. So now we had something else exciting to do. When 2 black holes collide, we don't think there should be any light emitted by that process. But these neutron stars are emitting gamma rays. They're emitting light throughout the magnetic spectrum. So we had to move very, very quickly to try and find the electromagnetic light counterpart to the gravitational wave. So there was a team in Santa Cruz that was working on this. They had very quick observations with one of their telescopes of nearby galaxies where they thought this could have originated from, and they were frantically looking through them to try and see if one of them showed a sign of the flash of light coming from this event. It's very hard to tell exactly where gravitational waves are coming from, so they had a big list of images to look through. And one of the researchers on the team had about the most understated response to this discovery ever. He sent a message around to the team that just said, "Found something." In one of the images, they saw the unmistakable sign of one of these events. So this was time domain astronomy. This was astronomy that had to happen quickly and also had to happen carefully. But it resulted in us discovering for the first time gravitational waves and light coming from an object in space, which was really just incredible. I've been talking a lot about weird discoveries and surprising discoveries and fast or fleeting or unusual discoveries. Sometimes this means something amazing, like detecting gravitational waves and light from 2 colliding neutron stars. Sometimes it's maybe a little less dramatic. Sometimes it can even be a little bit disappointing once you look at the real reason why. One example that I like pointing to are potassium flare stars. So we know that our sun will produce what we call solar flares. It's this eruption of material from the surface of the star, and it shows up to us like a little tiny brightening. Other stars will also behave this way. Stellar flares are fairly typical. And at the distances of the stars that we're talking about, the flare has to be very bright. So for years, studying stellar flares and understanding stellar flares was somewhat commonplace. In the 60s, at Haute-Provence Observatory in France, some astronomers were observing and taking data on a bunch of stars and analyzing the data as it came in. And they were extremely surprised by one of the results that they found. They saw a star that in its spectrum appeared to show a stellar flare that was very strong in a specific element. It was very strong in the element potassium. Nobody had ever seen this before. This wasn't a prediction of normal stellar flares. And they were really surprised. They were going, wow, we found a new type of physics. We found a new type of flare. We're seeing potassium flares from these stars. They wrote a research paper. It was really fascinating. And the community was really interested. They were going, okay, how do you explain potassium flares from a star? And it got better. 2 more potassium flare stars were discovered. In those discoveries, though, we started to see a little bit of a problem. Nobody else was finding potassium flare stars except for this team. And they were only finding them at this telescope. So another research group in California decided to look into this, decided to see if maybe there was some other explanation for what was going on. So to understand why, it's good to look at how telescopes like this are built. This is a very typical telescope design. It's known as a Cassegrain. Light will come down onto the primary mirror depicted in the bottom. It will bounce up to a secondary and then bounce from the secondary down to the detector that we're showing in blue. This can be a photographic plate. This can be a digital camera like we have now. It's a fairly straightforward way of gathering light from a telescope. The telescope that was being used in France was taking advantage of something called a coude design. In this case, we're bouncing off a couple of other mirrors along the way, and we're actually sending light to a detector in a completely separate room. There's good reasons for this. That travel that the light has to go through actually improves the quality of the image. And sometimes it's nice to have the detector in a completely separate room. In this case, that separate room was a nice little place where you could maybe go and take a break partway through the night. It's the 60s, it's France. Maybe you're taking a break and you decide to have a smoke break and strike a match. Potassium is the strongest element in the spectrum of match. So people at Berkeley figured out that this might be what was going on. They had an amazing research paper where they tried to debunk this, and it essentially involved running around the dome of one of the telescopes playing with matches and striking matches to see if they could reproduce a potassium flare. They acknowledge in their paper George Preston, who was the director at the time for authorizing their unorthodox use of the 120-inch Cadet spectrograph. The paper is amazingly thorough, by the way. They check book matches, they check kitchen matches, safety matches. They contacted the people in France who were, perhaps a little surprised that this was the explanation, but scientists at their core, and they said, hey, let's try our matches. There's a line in the paper explaining that there is no spectroscopic difference between French and American matches. And we now have a research paper that includes data on, the spectrum of a match. I assume that room in the telescope in France is now non-smoking. And you would think that the potassium flare stars had then been debunked. What's great is that a few years later, another observer was observing a star and did see excess potassium in the spectrum. And they took care to note in their paper that the explanation did not apply since the observer does not smoke. So potassium flare stars really are out there, but perhaps not in the manner that they were originally discovered. Another good example of this happened at Parkes Observatory, which is a radio telescope in Australia. And this has to do with phenomena called fast radio bursts and something called a periton. So during observations with this radio telescope, they detected a brief burst of radio emission. This was surprising. This was very interesting. We've seen gamma ray bursts, but a radio burst like this, and especially one on that rapid timescale, was really puzzling. Now, when they put this out, some responses started coming in going, oh, a flash of radios. Yeah, we see those all the time. There's lots of these. This is probably something really cool. We should figure it out. And they started digging into the data as a whole to see what these were. Now, those other detections were nicknamed peritons. And it was a sort of tongue-in-cheek nickname saying, maybe these aren't entirely celestial. Maybe we have some other explanation for this, but we don't yet know what it is. Now, the key came when you sort of step back and look at where the Parkes Radio Telescope is in the larger observatory. There's a couple of other buildings. There's a couple, dorms or administrative buildings. And in the paper that finally explained this, they noted that peritons were clustering around the lunchtime hour of the day. So everybody in here, I assume, has microwaved popcorn or dinner at some point. And you know how that goes. You're hungry, you're waiting, and you're looking at the microwave, and it's going 5, 4, 3, fine. And you just open the microwave door to stop it just a second or two before it's done. In old microwaves, doing that can sometimes cause a brief flash of radio waves that were being detected as peritons. So again, there is a delightful research paper showing how this happened. They tested all 3 microwaves on site. There's a paragraph where they probably learned more about microwave design than I think they ever wanted to in their lives. Microwaving a ceramic mug full of water, microwaving the same thing every time. But ultimately determining that, yes, that was what these peritons were. All of those detections were probably just flashes from microwaves, right? Most of them were. One of them wasn't. Fast radio bursts, again, are real phenomena. They are fascinating phenomena that we're still trying to understand. We are now detecting more of them. We know how to separate them from something like being impatient with lunch. And we're trying to figure out whether these are coming from stars, from objects that we maybe can't fully explain yet. They're a great example of a weird object in space, but one that was discovered in a slightly unorthodox manner. So, the last type of weird star that I want to talk about actually combines 2 types of stars that we've talked about before. I've explained red supergiants, what they are, how enormous they are, how cold they are, and how they work. And I've talked about neutron stars, these quantum physics-supported stars, tiny and sort of dead remnants of a collapsed massive star. There's really only one way that you could possibly make these weirder, and it's to stick them together. So if you imagine a red supergiant and a neutron star in a binary system, these are 2 stars that are orbiting one another and perhaps interacting with one another, exchanging mass, inspiraling closer and closer, kind of like those 2 neutron stars that we saw making a gamma ray burst. There's a really fascinating thing that can happen in a system like this. That neutron star can effectively be swallowed by the red supergiant. It can spiral in, settle into, and eventually replace the core of the red supergiant and make something called a Thorne-Zhitkov object. I found out about these for the first time around, I think, the year 2010. I'd been working on red supergiants for years, publishing papers on them and noticing some strange red supergiants or red supergiants that we couldn't perfectly explain. And in response to one of those emails, or one of those papers, I got an email from Anna Zhitkov saying, years ago, Kip Thorne and myself invented these theoretical models of stars, which is just fascinating all on its own, and asking if we were interested in trying to look for them. So Thorne-Zhitkov objects predict this neutron star core surrounded by a big, cold, puffy outer layer. They had predicted these back in the 1970s, but they'd never actually seen one. We had this rough idea of how they should work. You're imagining these two stars in a binary, two normal massive stars, two blue supergiants. The more massive of those stars, the one in the foreground, will collapse, undergo an incredible supernova, and what's left behind after the dust settles from that supernova is a neutron star. The companion of that star will start to expand, cool off, go from the blue supergiant to the red supergiant stage, and swallow the neutron star along the way. It's a scenario that absolutely seems like it could happen, and the physics saying that these stars should be stable seemed quite solid, but detecting them was a really big challenge. If I back out and look at this again for a second, remember, a red supergiant is the size of Jupiter's orbit. Neutron star, size of the city of Waterloo. So that neutron star cannot simply be seen inside the star. It's buried deep in the heart of the star. And from the outside, a Thorne-Zhitkov object will look exactly like a red supergiant, almost. We can take advantage of the fact that there's a neutron star in the core of that star to search for it in a very subtle way. So to explain this, I want to first remind you of that boiling convection that we see in these very cold, massive, big stars. If I were to take a slice through a star like that, you can see the surface of the red supergiant, you can see the helium-fusing core, and you can see that convective cell in the middle. If I now change this from the cross-section of a red supergiant to the cross-section of a Thorne-Zhitkov object, you can see a couple differences. One is that the core is now a neutron star. The other is that this star is quite cold. It's as cold as the coldest red supergiants that we know about. That means that that convective region is huge. It actually takes up the entire outer portion of the star from almost at the surface to almost down where the neutron star is. This means that we can see some really strange chemistry going on in the star. So if you imagine a packet of material traveling through that convective layer, it will get dragged down to that area right near the surface of the neutron star, where the temperature and the pressure are really extreme. In that region, protons start getting rapidly shoved onto the nuclei of atoms in that packet of material. And if you remember your periodic table, that means that these objects are starting to climb up the periodic table. Every atom is slowly increasing in atomic number. The thing is, material only stays there for about 1/100th of a second. So it'll be bombarded with protons for a little while, drift back out into the cooler, quieter parts of the star's outer layers, and start to undergo something called beta decay. It'll start moving back down the periodic table. Before it can finish that trip, it gets dragged back down to that lower region and bombarded by protons, and the whole thing happens over and over. This is a type of reaction that we can't expect in any other type of star, and it should produce a very distinctive chemical signature. We should see huge excesses of things like molybdenum and rubidium and lithium, things that we would not normally expect to see a lot of in a red supergiant atmosphere. So we decided to use this odd predicted chemical signature to look for Thorne-Zhitkov objects. I showed you what the spectrum of a red supergiant looks like before. This is a very nice spectrum, but in order to look for these little individual elements, we had to basically take observations that let us zoom in. We could zoom in on very specific small regions of the spectrum and look for the exact color that you would expect to see absorbed by something like molybdenum or lithium or rubidium. So you see again these little bites out of the spectrum coming from molybdenum atoms absorbing light at a very particular wavelength, or lithium or rubidium. This is what a normal red supergiant would look like, zooming in on these three regions and trying to look for these three elements. We observed about 70 stars, thinking you know what? Nobody even knows how much molybdenum is in a normal red supergiant. This is going to be step one of the project. We'll look at what normal stars are like, and then we'll start trying to move on. We'll survey more red supergiants, and maybe one day we might find a Thorne-Jitgov object. So out of 70 stars, 69 of them looked like this. One of them looked like this. Now, if you'll notice, all those little dips just got a lot bigger. That means there's much more molybdenum or much more lithium or much more rubidium absorbing light. That means that we're seeing excesses of these exact three elements, the elements that you would predict from a Thorne-Jitgov object in the spectrum. We were amazed by this. We looked at every aspect of the spectrum we could possibly think of, and we eventually had one of our collaborators say this, looking at the star, "I don't know what it is, but I know that I like it." When we compared what we had to the predictions of Thorne-Jitgov objects, it fit beautifully. So we now have what we think is the first candidate for detecting a Thorne-Jitgov object. I'm very careful to use the word candidate here. The existence of Thorne-Jitgov objects would have really profound implications for stellar astronomy. The fact that you can have a stable star with a neutron star for a core is really surprising. It gives us a new understanding of how stable stellar interiors could work. It came from a system like this, these two stars in a binary that merged. So it gives us a slightly better understanding of how binary stars can behave. And it's a great tool for making things like molybdenum and lithium. You'll hear this phrase that we are all made of star stuff, and stars really are factories for producing most of the atoms that we see, and most of the elements that we see in the universe. So a new way of making some elements is always fascinating. Because of this, we love to call our object a candidate. Extraordinary claims require extraordinary evidence. We have 3 little bites out of a spectrum that got bigger. It's extraordinary in its own right. These are very difficult measurements to make, and it fits perfectly with the predictions of theory. But we're very eager to get more observations of this star to try and find others like it, and to really try and piece together a more complete understanding of how something like a Thorne-Jitgov object could work. So I want to wrap up by leaving you with one last thought. I talked about supernovae tonight. I talked about these exploding stars and how unbelievably bright they are and how we observe them. Nowadays, we observe them by seeing those little dots that turn on in other galaxies. These represent violent explosions from massive stars, and in other galaxies, that's what we see. I like thinking about this supernova from the year 1054, this supernova that happened in our own galaxy, that was so bright you could see it in the daytime sky for 2 weeks, that you could read by it at night. We have last seen a supernova in the Milky Way like this in the year 1604. Because of how many stars we have in the Milky Way and how often we think they should die, we think we should have seen a supernova like this about once every 100 years. So by that measure, we're 300-ish years overdue. And I love imagining what it would look like if we had a galactic supernova right here in our own Milky Way go off tonight. If we walked out of the building and saw this in the night sky. It's a really fun thought experiment to do. I mean, at first, it might actually cause a little bit of panic. You're seeing something bright in the sky, slowly getting brighter and brighter. I think depending on the current geopolitical situation, you might get a little nervous. But once we'd established that it was definitely a supernova and nothing else, it would be really interesting. It would immediately get a hashtag. Nighttime hosts on shows would be talking about it. Every cell phone in the hemisphere would probably have a photo of it that somebody snapped. And I guarantee you that every stellar astronomer would just up and lose their minds, including me. I really hope that we get the chance to see something like this happen. I participated in the eclipse that happened last August, and it was a wonderful chance to see people from all over the US and all over the world flock to the path of that eclipse in the pursuit of astronomy and in the pursuit of loving something like astronomy. I think a supernova like this would do something similar, that very bright object appearing in the sky, something that you couldn't help but notice and something that you couldn't help but get curious about, would be a really interesting thing to study, and oh my God, the data we get will be amazing. So on that note, I'll go back to the slide that I had up at the very start of the talk. Remember, I promised you that you could name everything on this slide, and now you can. And on that note, I will say thank you so much for being here tonight, and I'm happy to answer any of your questions. Thank you.
All right. So let's open the floor to questions. There's a microphone right there. If you have any questions, just form a queue behind it. And, well, let's go to a question in the theater right off the bat. Away you go.
Great presentation. I actually have two questions, if that's okay.
Absolutely.
The first one is, I was curious about the gamma ray burst sort of forums that you have online. I was wondering, do you guys share the raw data in order to get the meta-analysis? In the medicine world, we've been kind of forced to do that, so I'm curious if you guys are doing that.
You know what? It sometimes depends on the type of data or the type of group. We will usually post results. So somebody will take the data and very quickly look and try to determine, for example, how far away it is. And then write a post saying, here's this object, it's at this distance. Sometimes you'll have a couple groups sort of racing to be first. But generally, if you email someone and you say, hey, I'm curious about this data, they'll either send you the data or they'll send you their analysis of it. So there's very much an encouragement toward collaboration. It just sometimes happens organically rather than as a default when the data come.
Fair enough. The second question is actually has to do with the gravitational waves and the fact that the one that you guys found, you guys got to observe the light as well as the gravity at the same time. Mm-hmm. So I'm not a scientist, or sorry, I'm not a physicist, so I'm just curious, which one would be faster? Because technically light goes through space-time, but gravity is space-time, so, you know, or...
This is a fantastic question. So it sort of has a two-part answer. In terms of which is faster, they're both traveling at the speed of light. And for something like this, it sort of helps to, I have a couple colleagues who are experts in this, but the way that I like to think of it is that the speed of light is almost a property of space-time. It's built in. It's not an extra speed limit that things have. It's actually part of our model of how space-time works. So both light and gravitational waves will travel at the speed of light. Now, we'll detect the gravitational waves first with the light following it, not because they're moving faster, but because that's the order in which the signals are produced. That gravitational wave signal happens first as part of the gravitational disruption of the two neutron stars colliding, and then the flashes that happen after, the gamma rays and other light that comes later, something called a kilonova, and emission of other light, will happen a little later because it's literally happening later in the event, not because it was just too slow.
Fair enough. So warp drives are possible then, right?
Very good. Let's take an online question. In the Thorn-Zitkow objects, what happens to the original core of the giant when it's replaced by a neutron star?
This is a fantastic question, and it's a question we, first of all, don't have a definitive answer to. We're just starting to study Thorn-Zitkow objects. There was a resurgence of interest after we thought we had found one, so we're still working on trying to model them and how they behave. But what we think happens is that neutron star will settle into the core of the original star, which is starting out by fusing helium in the core. By disrupting the core itself, we go from fusing helium in the very heart of the star to fusing helium in sort of a shell around the new core. The actual fusion itself will also be disrupted by being very near the neutron star and by other weird physics that's happening in the core. So that old core we think will sort of run out of fuel and peter out, but this is just one of several explanations for what we think might happen to it, and we're still trying to suss that out from models.
Excellent. In the theater.
The one star you talked about, Eta Carina, is a star, or star system, I should say, that I have heard of before from my online Earth and Space Science class that I'm taking this semester. What I've heard about that star is that when it goes supernova, and it will, its brightness will rival that of the moon. Is that true? And if so, how long will that last?
I think that could absolutely be true. The supernova that happened in 1054 was outshone everything except the sun and the moon, so I could certainly see something like Eta Carina behaving that way. You also mentioned an interesting thing that I want to make sure everybody else understands, because you were very careful in calling it a star system. And you're right, there are actually two stars buried in there, buried in that picture of the ejected material that we see. Both of those stars are tens of times the mass of our own sun, and we do think that a supernova from something like that should be very dramatic and very bright. If it gets as bright as the moon, it's hard to say exactly how long that would last, but it would be on the order of like maybe a week or 2 weeks. Supernovae will get bright very quickly and then start to fade very quickly. And there's actually a lot we can learn about the star and the chemistry of it by following how the supernova actually fades away. But that really bright period will last a couple weeks.
Okay. Thank you.
Good. Here's another online question. Polaris. Polaris is a rare star that won't last that long. Do we know how much longer it might last? It sounds wild that the near, relatively speaking, future, the North Star, might not be there.
So the good news is that the star will be there for a while. It's just changing evolutionary state. And it's hard to actually say where the star is in its evolution. Because yellow supergiants are so rare and because it's so difficult to study them as a result, we don't have a great formula in place for saying, oh, Polaris is going to last this much longer before it turns into a red supergiant, or it's exactly at this point in its evolution. It would be really interesting to find more of these stars, but what's hard is that without knowing the exact distance to a star, it's very easy to confuse something bright and far away, like a yellow supergiant across our galaxy, with something dim but nearby, like a star like our sun, a yellow dwarf. So we're trying to study more of these, and we'd love to be able to eventually answer that question, but we don't know yet.
Let's finish with one last question. Your excitement, passion for astronomy is infectious. When did you know that you wanted to study the stars?
I think I knew I wanted to be an astronomer when I was about 2, and I remember why. I have a reason. So I was 2 years old in 1986, which was the last time that Halley's Comet made a close pass of Earth. I have an older brother, Ben, who was 12 when I was 2, and he had a school assignment to observe Halley's Comet. So me and him and my parents all went tromping out into the backyard, and I'm sure I was a slightly fussy 2-year-old who was a bit bothered by the dark until they sort of pointed me up. And apparently I was fascinated, and from then on, people would ask me what I wanted to be when I grew up, and the answer was always, well, I want to be a ballerina or an astronomer, or I want to be a firefighter or an astronomer, and later on, a marine biologist or a paleontologist or an astronomer. But astronomer was always there, and astronomer stuck. I read A Wrinkle in Time when I was about 8 years old, and it just absolutely fascinated me. I was so amazed that we had this protagonist of a little girl who was into physics and into astronomy, and that and other books like that, and things like science activities in school really helped encourage this in me. And then when I went to college, I majored in physics, knowing that that was the starting path to becoming an astronomer, and did not look back from there.
Ladies and gentlemen, Dr. Emily Levesque.
Arthur C. Clarke had a sequel to 2001: A Space Odyssey. It's called 2010 Odyssey 2. And at the end of it, an alien intelligence converts Jupiter into a star. As a group of astronauts narrowly escape the implosion, they receive the following message from the aliens. All these worlds are yours, except Europa. Attempt no landing there.
Now, that was just a novel, but it suggests that already in 1982, we suspected that Europa might offer our best chance of finding alien life in our solar system.
42 years later, in October 2024, NASA is actually launching the most advanced mission to hunt for signs of alien life. And it's going to Jupiter's moon, Europa. There's just one problem. Jupiter kills everything around it. So how could life even exist there? And how do you make a probe that can withstand the perilous conditions? Deep inside Jupiter, there is so much pressure that hydrogen is believed to take the form of a metallic liquid. And this metallic liquid hydrogen generates an incredibly powerful magnetic field, almost 20,000 times stronger than Earth if you measure at the same distance away. So if you could see this magnetic field from Earth, it would appear twice as big as the full moon. On its own, that magnetic field is harmless. But right in the middle of it is the most volcanically active world in the solar system, Jupiter's moon, Io. The volcanoes on Io's surface shoot out tons of sulfur dioxide, and every second, 1 ton of this material gets ionized and trapped inside Jupiter's magnetic field. And the field accelerates these particles to rotate incredibly fast with Jupiter, so they whiz around at over 300 kilometers per second. Their inertia actually pulls back on the field, stretching it out, and this trapped material slams into other moons, ejecting even more particles from their surfaces. This cycle forms massive radiation belts which span past Europa and the other moons of Jupiter.
Now for electronics, this intense radiation is kryptonite.
In the 1970s, the Pioneer 10 and Voyager missions only briefly passed by Jupiter, but the radiation caused glitches, gave the instruments false commands, and corrupted some of their data. Even with modern shielding, a spacecraft within the radiation belts would only survive for around 3 months. So how will NASA's new mission, the Europa Clipper, orbit Europa for over 4 years without getting fried? Well, the solution is it won't.
It'll orbit Jupiter from afar and then swoop in every few weeks to quickly fly by Europa and then leave again. And since the mission is going to collect a lot of data, it can use the downtime while it's way out here to transmit it all back to Earth before going in for another swoop. In all, it'll do 49 flybys, mapping almost the entire surface. That's actually how the Clipper got its name, after the fast and nimble 19th century clipper ships, quickly dipping in and out of ports. But of all the places in the solar system to look for life, why Europa?
If you stood on Europa's surface, you'd be hit with 5,400 millisieverts of radiation in a single day. That's 1,800 times more than the annual dose here on Earth. If you stay here for a couple hours, you would eventually die from radiation sickness. But Europa contains a secret. When Voyager 1 passed by Jupiter in 1979, it took this photo of Europa. If you compare that to most of the other moons in the solar system, you'll notice something is missing. Craters. Every planet and moon has been bombarded by asteroids over billions of years, and most planetary surfaces show it. But not Europa. So why not?
Well, something recent, say over the past 60 million years or so, must have been happening on Europa to erase most of these craters from the surface.
16 years after Voyager, Galileo arrived to Jupiter. It spent 8 years studying both the gas giant and its moons. And Galileo's magnetometer picked up something interesting on Europa. Jupiter's magnetic poles, like Earth's, aren't aligned with its geographic poles. So as the planet rotates every 10 hours, the whole magnetic field wobbles. This changing field from Jupiter induces a magnetic field on Europa, and a relatively strong one at that. That means there must be an electrically conductive layer within Europa that reacts to Jupiter's field. And readings from Galileo indicate that it must be somewhere close to the surface, only tens of kilometers deep.
So what kind of conductive layer?
Well, Europa's white surface is almost entirely covered in a thick crust of water ice. These reddish-brown regions, when observed through a spectrometer, fit the description of a lot of things, like hydrated salts, sulfuric acid, or even bacteria. We need more data to be sure, but recent experiments at JPL found that sea salt, when bombarded with intense radiation, turns from white to this same brownish color found on Europa. So scientists suspect that there's a whole saltwater ocean inside Europa. It could be 100 kilometers deep, meaning Europa would contain twice as much water as the whole of the Earth.
And it must be driving geological activity that constantly smooths out and renews the surface of the moon. But the Jupiter system only gets about 4% of the sunlight we get here on Earth. So Europa's surface is constantly below negative 160 degrees Celsius, so you'd expect the whole ocean to be frozen solid. But there's a way to generate heat that doesn't rely on the sun. And I've got a little demo here to prove it. Europa's orbit around Jupiter isn't a perfect circle. This is because Io, Europa, and Ganymede are all in orbital resonance. Each time Ganymede completes one orbit, Europa completes 2, and Io 4. Because of that, Io tugs Europa inward on one side of the orbit, while Ganymede pulls it out on the other, making its orbit more eccentric. Now, Jupiter's pull is stronger on the closer side of the orbit than on the farther side, so Europa is constantly being stretched and squeezed, stretched and squeezed. And you can see how this rubber ball gets warmer as I squeeze it. Scientists believe that the friction caused by the tidal flexing of the entire moon can generate enough heat to keep the ocean liquid. This effect gets stronger the closer you get to Jupiter, which is why Io is so volcanically active. So you can see this ball is significantly hotter now. I held onto this ball at the same time to make sure it wasn't just the heat coming in from my hand. What sort of temperature of the ocean are we thinking?
So it depends on how salty it is. So melting temperature of ice, or maybe depressed by 10 degrees Celsius below that if it's a very salty ocean, similar to cold oceans on Earth.
And how would the flexing differ if there's this big liquid ocean versus if there's no ocean there?
If there's no ocean, Europa should flex by only about 1 meter in amplitude. But if there's an ocean in there, then it flexes with an amplitude of 30 meters. So that's an enormous deflection, and that will come out pretty clearly in the gravity data. Another argument for how thick the ice shell is, we see these very strange features on the surface that are arcuate in shape, but like multiple arcs put together. We call them cycloids, and not something you'd expect to see on an icy moon. And we think they form if a crack propagates at just the right speed, about the speed someone would walk, and is following the changing stress field of Europa being squeezed as it orbits around Jupiter. And if there were no ocean down there, there wouldn't be enough of an amplitude of that motion to explain the cracking. But if there is an ocean, then it could explain the cracking.
All that tidal flexing pushes magma in the outer core up, closer to the seafloor. Water flowing through the crust above it is heated and it picks up minerals from the ground, ejecting them into the ocean. This creates hydrothermal vents. And where we find these on Earth, we also find life. Thousands of meters below the surface with no sunlight, these vents are oases for ocean life. The life forms down here rely on unique bacteria that feed on the minerals from the vents, rather than from the energy provided by the sun. How long are we thinking that Europa has had an ocean?
It could be 4 billion years. We don't know for sure.
That amount of time could give life the opportunity to evolve in those oceans.
Right, exactly right. Organisms can use methane, carbon dioxide, sulfur reactions. Any chemical reaction you can think of that might happen in the ocean can potentially be used as a fuel for that organism's metabolism. So we're not talking about searching for fishes or whales or squids or something down there, but looking for single-celled organisms.
We were so concerned there might be life on Europa that when the Galileo mission was ending in 2003, it was deliberately crashed into Jupiter to avoid the risk of contaminating Europa. But Clipper will not be able to drill through the kilometers-thick ice crust. So how are we going to find evidence for life beneath that thick surface? This is the Snotbot. It's a drone with petri dishes glued to the top, and it flies right through whale blows to collect whale snot right here on Earth. And zoologists can use the Snotbot to retrieve all sorts of info on a whale's biology.
And it turns out we can do something very similar for celestial bodies too. We've actually captured images of water geysers shooting out of Enceladus, a moon of Saturn, housing a subsurface ocean. And the Hubble Space Telescope has picked up some evidence of what could be similar geyser eruptions on Europa. The hope is that Clipper could fly through one of these plumes like the Snotbot and reveal their chemical composition using a mass spectrometer.
But evidence for an ocean on Europa isn't conclusive. Enceladus seems like a stronger candidate. We have actual images of its plumes, and we've even flown through them. We are almost 100% certain there's a subsurface ocean there.
If we have these plumes on Enceladus and there's clearly maybe a liquid ocean there, why does Europa have your attention more than Enceladus? Is there something that draws you?
We don't know how long it takes life to get going, but it's possible that Enceladus may have just kind of started up its engines, whereas Europa has more likely been well evolved over a long time.
Surprisingly, being bombarded by Jupiter's radiation actually makes Europa a better candidate. See, those high-speed particles hitting Europa's surface give water and carbon dioxide molecules enough energy to form new compounds, like formaldehyde or hydrogen peroxide. And these can serve as food for life beneath the surface, if they can get down that far.
And we have evidence of overturn of the icy shell at chaos zones where the icy crust seems to have collided and material has been shoved into the icy shell. So there may be ways for this fuel for life to get down into the icy shell and potentially to the ocean.
And Clipper doesn't have to touch down on the surface to confirm this.
There's an infrared spectrometer to look at the chemical fingerprints of light bounced off the surface to help identify and map out where the salts are, find if there are organics there. There's a ultraviolet spectrograph that's aboard the spacecraft to look for plumes. Are they there? And of course, then can we fly through them? And then there'll be imaging of essentially the whole globe at better than 100 meters per pixel resolution. So one camera will take swaths of images as we fly over the surface, and that's called the wide-angle camera. And then the other camera is the narrow-angle camera. From 50 kilometers altitude, it will get half meter per pixel images, right? So it'll be able to resolve my desk here if it were on Europa. And then it would be a future mission, like a lander, that would go and actually search for signs of life at Europa.
Do you think a lander would have a chance of survival?
There have been studies that say we can get a lander living on the surface for a month if we think that's sufficient to go in there, scoop some stuff up from below the depth of radiation processing and put it into a mass spectrometer and see what we see.
But the Europa Clipper won't be studying Jupiter's moons alone. The European Space Agency's JUICE mission, or the Jupiter Icy Moons Explorer, is already on its way to Jupiter. It will come to the system just 15 months after Clipper, and it'll even be doing a few flybys of Europa before settling into a tight orbit around Ganymede.
So the European Space Agency will also have a mission there at the same time?
Yes. We're having informal conversations with members of the JUICE science team. What would it mean to have two spacecraft there at the same time? The JUICE mission will end up in orbit around Ganymede, and Ganymede has its own magnetosphere. Well, we'll be outside Ganymede's magnetosphere, so we might say, oh, look, there's this big burst coming from Jupiter, and then JUICE might say, oh, we felt that over here in our magnetic signals. So we wouldn't have to really do anything different except talk to each other and make sure that the sum of the whole is even bigger than its parts.
Europa Clipper was scheduled to launch on October 10th, 2024, but NASA is waiting for Hurricane Milton to clear Florida before the spacecraft can take off safely.
When will we get the first results?
You'll start seeing distant observations coming in 2030 as we look at Europa from afar and search for plumes, and then you'll see the first really high-resolution data in 2031.
So after, say, 26 years of thinking about a mission to Europa, how does it feel to be so close to launch?
It's a little surreal, I must say. This has been such a long time coming. It's occasionally hitting me that our spacecraft is going to be up there in the heavens, right, on its way.
It turns out that during a Europa Ocean conference in the late 90s, NASA actually video called Arthur C. Clarke, and after showing him plans for a future mission to explore the faraway ocean world, Clarke finally gave NASA permission to land on Europa.
Hello wonderful person, this is Anton, and in this video we're going to be talking about one of the most unusual planets in our solar system that you see right there behind me. This is Uranus, and some people think that it's a relatively boring planet. On the other hand, some people, or some scientists specifically, think that this is actually one of the most unique, most fascinating, and most unusual planets in our solar system. And there are definitely quite a lot of reasons for why they think so. So for one, even though it seems kind of featureless and doesn't seem to have much happening on the surface, this is because it's actually only invisible light. If you were to look at it in the infrared, you would actually see something completely different. Specifically, you would see something like this. You would see a very unusual looking planet with a very sort of minor but still visible ring around it. But that's not really what we're talking about today. What we are going to be talking about is why this unusual planet also has a very unique way of spinning around compared to other planets in our solar system. In other words, why is it that Uranus has such an unusual rotation around its orbit? Because actually, if you were to compare it to other planets, it seems to be rotating completely on the side. Now, we briefly actually talked about this phenomenon in one of the previous videos from many years ago, but today we're going to talk about a new study that actually used a very realistic and very accurate simulation to actually finally answer this question once and for all. So let's talk about why Uranus seems to be spinning on the side. Now, first of all, what we know about Uranus is actually already quite extreme. For one, we know that its magnetic field doesn't seem to correspond to its rotation almost at all. The magnetic field right here is about 59 degrees away from the spin of rotation, and that already shows us that this is actually a really strange planet. On the other hand, we also know that its composition on the inside is quite different, and it actually seems to even have what's known as diamond rain, essentially diamond-like particles raining down in the atmosphere. On the other hand, it's the only planet that doesn't seem to actually generate any heat on the inside, and is basically the coldest planet there is. But all of this, for the longest time, suggested that this may have been because of a very major collision that happened something like 2 to 3 billion years from today. And the simulation that I'm going to show you investigated this by using what's known as smooth particle hydrodynamic simulation, developed back in the 70s to study various astrophysical problems. And it's often actually used in various fields, including ballistics, volcanology, and oceanography. And a lot of these findings are from a scientist by the name of Jacob Kejeris from Durham University. Essentially, what they did for this study is run close to 50 simulations using a supercomputer until they found this one that seems to have corresponded to a major collision from an object that was about 2 to 3 masses of Earth that created this. And that, in a sense, caused the actual rotation of Uranus to flip by about 97 degrees, which actually is what we have in real life as well. And interestingly, if you actually look at the time here, it only took a few hours for Uranus to basically completely stabilize its orbit and to shift almost entirely by this amount. So here, within about 62 hours, it's back to being stable, very planetary, and even have its moons shifted by about 98 degrees. In other words, if we try to recreate this in Universe Sandbox, and if we actually look at Uranus right here, with obviously its moons added as well, you'll notice that the moons are also orbiting at the same sort of inclination. And all of this can be explained by a relatively major collision with a planet that was about 2 times mass of Earth. Now, it didn't seem to actually collide where the mass would be added to the total mass of Uranus. As you can see, the vast majority of the planetary mass actually gets expelled. And this suggests that the original mass of Uranus hasn't really changed that much. And so here we can maybe try to recreate this by colliding an object similar to two masses of Earth, and actually seeing what would happen to Uranus in our simulation if we did the same as what may have happened in real life. So here's two masses of Earth, and it's going to pass relatively close to Uranus, and we're going to see if it actually shifts it even more in terms of the actual obliquity, which is the value that we're trying to measure here. Obliquity refers to the difference between the actual rotation angle and the actual orbital plane. And so this is maybe what have happened here. Here's our Earth approaching Uranus, and let's see if it actually changes the obliquity again. Now, I tried to kind of put it in a position where it might just briefly, okay, it wasn't really brief. It wasn't supposed to completely collide with Uranus. It was supposed to just briefly pass, just like it did in the simulation. But as you can see here, it did change the orbit and also the obliquity quite dramatically. Although not actually by as much as it did originally. Here it changed by about, I think, 12 degrees. But it also changed the orbit. So if we now look at the orbit of New Uranus, its orbit actually shifted even beyond the orbit of Neptune. So these collisions most likely happened quite a lot in the days of early solar system. And during the so-called late heavy bombardment, we think that pretty much every planet has some sort of a collision. We know that Earth actually may have received a collision which created our moon. We know that Mars received a collision kind of flattening the northern parts. Venus received a collision changing its rotation as well. And Mercury seems to have received a collision as well. And also Jupiter, Saturn, and Neptune. We don't really know how it influenced all of these planets, but for Uranus, we have now simulated it using the top-of-the-line supercomputers, and we think that basically this is kind of how it happened, and this is what led to Uranus becoming such an unusual planet with such an unusual orbital spin, but also with unusual features such as being the coldest planet, the planet with no heat on the inside, and of course the planet with one of the strangest magnetic field as well, specifically a very tilted magnetosphere with a very unusual shape. Now, all of this suggests to us that we need to actually send a mission here, because there's probably going to be a lot of really interesting things we're going to discover. The only mission we've ever actually had that passed by here was back in 1986, when I was basically still a toddler. The Voyager 2 mission actually did visit and took those photos, and every other photo since was actually by a telescope, either by Hubble or Keck telescope or a few other telescopes that have actually taken very unique but also not super accurate pictures. So we do need to have a mission here to actually try to discover what else we can find around this unusual ice giant. Uranus is definitely mysterious, and there's definitely a lot of things we're going to be discovering here in the next few decades. On that note, I wanted to actually finish this here, so now hopefully you know a little bit more about Uranus and its unusual tilt and how it's acquired it over the past 3 billion years.
We'll move on to closing with a couple of minutes about things that you might not know about Albert Einstein. And this is from the Open Mind knowledge sharing community. And with that, I'll close the November meeting, and we'll see you again in the new year for the monthly meeting. Thank you.